I have debunked so many skincare myths, and for a lot of them you might think it is really obvious that they're wrong. But the reason they spread? They sound like they might be true. So some of the myths I've debunked are myths that I used to believe. So in the spirit of learning and growing and becoming generally better people, let's talk about skincare myths I used to believe, why they're wrong, and what to do instead. I'm Michelle, chemistry PhD and skincare nerd who is slightly obsessed with myths because I just hate doing things that don't actually help me get to my goals. So as we're going through these myths, I'm also going to talk about why I believed them in the first place, because correcting these processes is how we stop falling for more. Let me know the myths you believed in the comments, and let's start today's meeting of Critical Thinking Club. This first myth is a bit embarrassing. I used to believe that chemical sunscreens needed to absorb and bond with skin to work, and that meant you needed to wait 20 or 30 minutes for chemical sunscreens, whereas mineral sunscreens would work straight away. And you should also wear less products under a chemical sunscreen. This is not true. Chemical and mineral sunscreens both work straight out of the bottle. There's no special activation time. You can test this on paper if you have a UV torch. With white paper, there are brighteners in it that glow under UV light. If you smear some chemical sunscreen on it, then you can immediately see that it goes dark because it's blocking UV from shining through to the paper. Mineral sunscreen also blocks UV from shining through, but moisturizer doesn't, and so it doesn't change that glow too much. In my defense, I believed this in 2011. There wasn't that much skincare information out there. The main things were Paula of Paula's Choice and Beautypedia, and there was also a website called Skinnation which had this myth on there. We were all just stumbling around in the dark. I don't think I ever spread this myth myself, but it is for another embarrassing reason. I didn't find a sunscreen I could wear consistently until maybe 3 years into blogging. I know. So because of that, I just didn't post that much about sunscreen. By that point, I'd started talking to Stephen Coe of Kind of Stephen and Poems from the Lab, and I learned a lot from that. He really opened my eyes to how many skincare myths there were and still are. Even now, I see this everywhere. It was in a recent peer-reviewed article in a journal for Australian doctors, along with a whole bunch of other sunscreen myths. Now, you might be wondering, if this is a myth, why do sunscreen bottles say you need to apply 20 or 30 minutes before you go into the sun? First off, this is also on mineral sunscreen packaging, so it's not about chemical versus physical. The actual reasons are, all sunscreens need time to dry down so they don't rub off as easily when you put on clothes or move around. And this is also why you should wait a bit before you apply makeup over sunscreen. The other reason is to avoid people driving to the beach on a sunny day, then walking to the beach, finding a nice spot, putting down their towel, stripping, and then applying sunscreen. Because by that point, you've already gotten tons of DNA damage, you might already be sunburnt. This next myth is super widespread, and I think every scientist or doctor who's ever gotten into skincare has probably fallen for this, at least at the start, unless they were extremely lucky. I used to read a study, and if it said 2% niacinamide had particular benefits, I would go off and look for a 2% niacinamide product. If it was lower, then I thought it wouldn't work. And I really should have known better because my background does have pharmacology and drug development. But sometimes it's really hard to join the dots between things you learn in one part of your life to a different part. The reason you can't just look at percentages is that 2% is just how much they put into the product. It isn't how much actually ends up going into your skin. First issue is stability. Not all actives are stable, so some of it might decompose before you even get it out of the bottle. And this is not regulated for cosmetics. There was a study on retinol that found a lot of formulas had way less than the listed percentage because retinol can break down really easily. And then when you put it on your skin is a really good barrier, so with a lot of ingredients, most of it will stay on the surface and only a fraction gets in. Both of these depend on the formula. There are lots of ways to stabilize active ingredients like adding antioxidants. Also encapsulation, which is sort of like putting it in a little popping boba with a protective outer shell. There's also packaging. Some packaging is more protective than other packaging, like Stevens Super Stable Vitamin C, which is in a really airtight tube. Actually, that is another myth that wasn't on my list for today. Airless pumps actually let in quite a lot of air. There are lots of gaps. You can actually get better protection if you have a really good tube. Anyway, after stability, there's also lots of different ways of getting something into the skin. For example, you have penetration enhancers. Some of these can mess up the skin barrier a bit and help the ingredients get in. There's also things like solvents and delivery systems. Why do so many people believe this? I think part of it is skincare marketing has so much fluff. Sometimes it feels like the only things you can really trust are the ingredient list and the percentages of anything in the product. I think another big factor is this is how medicines work, and a lot of peer-reviewed skincare info is written by medical doctors like dermatologists. With medicines, you can usually go, well, brand name Nurofen is 200 milligrams of ibuprofen. You can just buy the generic version and that should really work the same. But the reason you can ignore the formula like this is because drugs are regulated differently. They're regulated for stability, they can't break down much before the expiry date, and they're regulated for something called bioequivalence. Basically, before a generic drug is approved, they need to have evidence that it's going to work pretty much the same. For oral medications, they usually look at how much of the active ingredient will absorb into the blood and how quickly, and then for creams that you put on skin, usually they put the cream on a skin model, which is like a little membrane, and they see how quickly the active ingredient will get through. And even with this level of testing, generic drugs don't always work the same. So with skincare products which don't have all this extra regulation, a product with 1% of an active ingredient could work as well as a product with 5% if it has a better formula. So what should you look at instead of percentages? Well, percentages are still useful, but they don't tell you as much as clinical testing. And a lot of the time, clinical testing claims sound kind of questionable. You'll see things like 95% of consumers felt that their skin looked smoother. It sounds really fluffy. But there is actually a really good reason for this fluff, which I might talk about in the next installment of this series. Let me know if you want me to go into more detail. But before we do that, let's talk about one of my favorite skincare products. Peeling gels peel off skin. This is a myth, but this tends to be how they're marketed. There are a bunch of brands who do like demonstrations in shopping centers. They'll say like, oh, look at all this skin coming off, it's super effective. There was a bit of a debate about this back in the day. I don't think I ever really believed that it was all skin, but for a while I did think a decent amount of it was skin. One of the observations that I found pretty convincing is if you use it on your skin, the first time a whole bunch balls up, but then if you do it again, you get a lot less. And this would make sense if you do have less skin on your face to get rid of. And I think someone on Reddit might have tried it with a glove on a plate and they didn't see anything bunch up. I didn't understand what was happening until I tried doing it myself. I think actually testing things is really underrated because you end up noticing interesting stuff that gives you hints about what's going on. But it's also why I don't do a lot of experiment videos because I never know how long they're going to take. Like testing the heat protectants and the sunscreen sprays, those were meant to take like an hour. They ended up taking like 30 hours or something. Anyway, I tried rubbing the peeling gel while I had gloves on so it wasn't touching any skin, and it really didn't react like it did on my skin. Normally I get tons of rolls after like 5 seconds, but then after half a minute, I only got a few pretty pathetic looking rolls. So I started thinking, what is different between the glove and my skin? First, I tried blowing off the water because it does seem to get dry faster when you're using it on skin, and that helped a little bit, but it wasn't really bunching the same. But then I realized the ingredients of peeling gels are really watery. Oil doesn't play with water, it could cause weird textures, and skin has oil. And this seemed to be the answer. Once I added a drop of oil, all the peeling gels I tested started bunching up. This would also explain why you get less rolls when you use it a second time, because after the first time, a lot of that oil has come off onto the rolls and into the water when you're washing it off. A bit of it is probably skin, there's usually like little dark bits in them, but almost all of it is going to be the product. And this is a good thing because if you had this much skin coming off every time you used it, that is pretty disturbing. You do need dead skin cells at the top of your skin. It is protecting like your insides. So peeling gels are actually really gentle physical exfoliants. Instead of using scrubbing beads, it's using these soft rolls that sort of feel like a disintegrating wet tissue. I find them really good for keeping on top of clogged pores, also dealing with tretinoin peeling. They also help break off like dead skin flakes around my nose when I have a cold or allergies. And this is really good before putting on foundation. I would usually get tweezers and like pull off those flakes, but that is much more damaging. I also find them more thorough and less harsh than a standard scrub. So I am a huge fan of peeling gels. I think they are a really underrated product, but they do tend to be marketed in this really gimmicky way. I don't know, justice for peeling gels, I guess. Next myth, hyaluronic acid holds onto 1,000 times more water. Again, this one is a mix of me not applying stuff I learned from chemistry to skincare and authority bias, trusting peer-reviewed literature too much. This is why I go on so much about how if something is peer-reviewed, it doesn't mean that it's true. This is another myth I used to believe, and again, shout out to Stephen for really opening my eyes to this. For the longest time, I thought I never fell for this hyaluronic acid myth. Pat on the back, it is obvious that there's no space around hyaluronic acid to fit all that much water. But then a couple of people contacted me about having this myth in a blog post from 2016. 1 gram of hyaluronic acid can hold onto 6 liters of water, and that is actually worse. Like and subscribe to learn from all my failings. I got this factoid from this reference. It's a safety assessment of hyaluronic acid in the International Journal of Toxicology. The authors are the Cosmetic Ingredient Review Panel. These are the official group of scientists who look at the safety of cosmetic ingredients. They are like the US version of the SCCS. They have lots of expertise and experience, and in the introduction it says, 1 gram of hyaluronic acid can hold up to 6 liters of water. Now, if we follow the reference trail, reference 9 is this, and this says, the water binding capacity correlates with the molecular mass and can be up to 6 liters of water per gram. But there's no reference here, so this article doesn't actually back it up. So why did the CIR mess this up and the peer reviewers not pick it up? Well, it's because introduction sections aren't really where the real science is in a paper. This article is about toxicology. This little part is just giving like colorful background info, sort of like fun facts. After doing all of the hardcore toxicology calculations and discussion, that part is new and that's what they're responsible for. I'm sure they checked all that like a million times. They are probably just skimming this part, and something that sounds kind of right is good enough. They were expecting people to read this and cite it for the stuff they actually did, not for some random thing in the introduction. This is actually a massive problem in the peer-reviewed literature, because even people who are writing peer-reviewed articles are making this mistake. I mean, the paper that the CIR cited for this is about different uses of hyaluronic acid, and that little fact is pretty much also just jammed in there for vibes. Interestingly, I found this little snippet. In 2023, the CIR looked at hyaluronic acid safety again, and in the meeting transcript, one of the members questions this for like a second and then they move on to something else. Anyway, there is a neat article from 2024 from some chemists who went off and tested this myth, plus they went back and traced the origin of it. They give examples of how widespread it is. They look at the peer-reviewed literature, they talk about the CIR review and the reference that they used. Also, they looked at dermatologists, Harvard scientists, ingredient suppliers. They don't roast me, which is really nice. Thanks, guys. They tried to trace the claim and they didn't find any good evidence for it. But they think it might come from a finding that hyaluronic acid can sort of like sweep water along with it. Like if you sweep your hand through water, you can get a lot of it to move, even though most of it isn't like binding to your hand in any sort of way. But the way that chemical binding works is that the water needs to be basically touching the hyaluronic acid to form a hydrogen bond. This is not hyaluronic acid, this is glycerin, but it's the same concept. And around the hyaluronic acid, there's only really enough space to fit about 1.5 times the weight in water. In the experiment, they mixed 1 part hyaluronic acid and 1,000 parts water, and they ran some experiments to look for any sort of noticeable binding between them, and there wasn't enough to be detected. Then using other people's data, they calculated that hyaluronic acid actually holds onto about 40 to 85% of its weight in water. They also mentioned that there are polymers that hold onto a lot more water, like polyacrylates. These can hold onto 300 times their weight, they're used in nappies, and they give products a thicker texture. They conclude that hyaluronic acid doesn't have any mind-blowing water-binding properties that make it an extra good humectant, but it could still be useful in products. And I would add that since polyacrylates bind tons of water, but they aren't really great humectants, good humectants probably need to be able to bind water, but more water doesn't mean better. The reason glycerin seems to work so well is because it's actually not that much bigger than water. I know it looks really different here, but in the grand scheme of things, these are similar. So glycerin can actually go through water channels in skin called aquaporins. It can get to places that other humectants can't. With hyaluronic acid, some types seem to work as signaling molecules. They're active skincare ingredients. They don't just work as humectants. Here is a related myth. Hyaluronic acid sucks water out of your skin if you don't use an occlusive moisturizer afterwards, especially if you're in a dry climate. Or that you need to apply hyaluronic acid to damp skin and not dry skin so it has water to hold onto. I didn't really believe this for hyaluronic acid specifically, but I remember seeing this a lot in dermatology textbooks, and it sounded like it could make sense until I really questioned it. Again, the reason is hydrogen bonds. Hydrogen bonds are how humectants would be grabbing onto water, but hydrogen bonds only work over a really short distance. They have to pretty much be bumping into each other. The humectant is working more like sticky tape and not a magnet. There is no long distance pulling effect. If the humectant was sitting on the surface of your skin and grabbing onto water that's bumping into it, then that water was evaporating out of your skin anyway. We actually have water evaporating through our skin all the time. It is called transepidermal water loss. This is what occlusives are trapping, and humectants sitting on the surface are essentially doing the same thing. They're trapping water but in a different way. Also, a serum is at least 80% water. Moisturizers are usually at least 70%. These are quite low, it's usually higher. There is enough water in the product already for the humectant to grab onto. Adding extra water by having damp skin is not going to make much of a difference. The Ordinary actually ran a clinical study to test the dry versus damp skin thing. They sponsored me to do a post about it a couple years ago, which I thought was really cool. This video is not sponsored, I just wanted to talk about this again because it is such a common myth still, and I think it is cool that The Ordinary went off and ran this sort of test. So few brands do stuff like this. They tested their 2% hyaluronic acid and B5 serum on dry and damp skin, and it worked around the same on both. Plus, it's not drier after using hyaluronic acid. But unsurprisingly, it works better if you also have a moisturizer on top, but also there's no difference there between wet and dry skin. So why do people think it dries their skin out? Here are some possible explanations. First off, they are not using a moisturizer as well as a hyaluronic acid, and their skin actually needs moisturizing. In general, a well-rounded moisturizing approach works best. You want a mix of humectants and occlusives and emollients. If you just have humectants, that isn't really going to cut it if you have dry weather. You can't expect it to do that much, especially when the amounts of hyaluronic acid are going to be pretty low. It could also be that if you have hyaluronic acid and thickeners in a product, they can form a film on your skin. And as that film dries, it can contract a little bit. It's sort of like the skin on soup. So that tightening feeling could feel like your skin is dry. But it's not like damp skin is bad. If you prefer using it on damp skin, that is fine. I think it does have a benefit in that when you have extra water, then you're increasing the amount of stuff that you have on your skin to spread. So it can be easier to spread it out. It's similar to when you have a tiny amount of tretinoin. If you put a moisturizer on first, then you can spread it out more easily. But if you prefer putting it on dry skin, then keep doing that. If you feel like your skin is drying out, maybe look at adding a moisturizer. I talk about more moisturizers in my basic skincare guide. So what have we learned today? I guess the big overarching lesson here that also applies outside of skincare. It is really easy to nod along to things that sound right, especially if they're coming from an authoritative source like a peer-reviewed article or a textbook or a lecture. This is just part of human nature. It is our cognitive biases. These are mental shortcuts that help us make sense of the world and survive. But they don't always work, and they lead to tons of myths that get passed along. And hearing myths repeated also makes us feel like it is more true. This is another effect called the illusory truth effect. If something is easier for us to process mentally, it seems more true, which is the case if it's something that we've heard before. So we need to stay open to questioning our own assumptions and going, hang on, is this thing I've heard a million times from people who really sound like they know what they're talking about? Is it actually true? And this, of course, also applies to questioning what YouTubers and science communicators say as well. These cognitive biases are also a massive issue with AI slop. It sounds really confident and the grammar is usually pretty perfect. So that feeds into authority bias and the illusory truth effect. But AI slop is a rant for a different video. Let me know what skincare myths you believed in the comments. Let's be embarrassed and become better people together. Like and subscribe for more critical thinking and beauty science. More videos are popping up around me if you want to nerd out more. See you next time.